Good morning, students. So I just got done grading the study guide, and unfortunately, not a lot of you completed it, but also a lot of you seem to have issues with parts of it. Now, I graded it based on were you trying, and so if you see your grade and it's really low, it's probably because you just didn't do part of it. But I also saw a lot of issues with the content. And part of that is because this unit, that is normally rather short, has been stretched out longer than it ever has been before because of these Zooms. So today what I'm going to do to try and help you all is I'm going to go through this entire document and make sure that you guys understand it. I'm going to make sure my software is recording the correct screen. Yep. But I'm going to go over this with you guys. Hopefully it'll make a little more sense. If you have questions, feel free to comment. Or just ask me in class next time I see you. Remember today, which is Wednesday, October the 7th, you're supposed to complete the test today. But I'm hoping that by going over the study guide, and I'm hoping you'll watch it, it'll help you understand some things a little bit better before you take that test. So anyway, here we go. Let's get started. Let me get this little box to go away, because I don't need that. All right, so here we go. Identify each of the following as metals, nonmetals, or metalloids. Well, if it says it's located on the left of the stair step, I already know this is the metals. The next one, it says located along the stair step. I know these have got to be the metalloids. And then the last one, by process of elimination, is going to be nonmetals. More people skip this than I would like to admit. Doesn't make sense to me. That took me all of about 5 seconds. But also look at that information on there. This is straight from the blank sheet review that I did with you during bell work or right after bell work yesterday. So I don't really know what to say about that. Next one, it says fill in the blanks using the words provided. One of the most important reference tools in chemistry is the periodic table. Duh. Okay. Oop, it moved. Let's try it again. It is organized based on common characteristics of elements, probably. Get rid of that. Families or groups are the up and down columns. Okay. There are 7 known periods, or 7 known rows, I think is probably what that's supposed to be. 7 known rows on the periodic table called periods. So there we go. All right, done with that one. Let's move on to the next part. It says fill in the blanks in the table below. So for this section, okay, we are going to be filling in this information. We're going to have group names, group number based on the AB system, oxidation number, and number of valence electrons. And this is also something I went over during the blank sheet review yesterday. And sadly, a lot of y'all were still just not getting it. Group number based on 1 through 18. I know that alkali metals are group number 1. Okay, it's these elements right over here. Okay, so it's these elements right over here. Group number 1. That's also known as group Roman numeral 1A. Now, the oxidation number, which if you've forgotten, I'm going to draw this right over here again, because some of you are still not remembering it. On the periodic table, we have 18 different columns, and I've actually mentioned that before. So we have group 1, 2, skip a few, 3, 4, 5, 6, 7, and 8. But these over here, 13, 14, 15, 16, 17, and 18 is actually what those are. But your valence electrons you actually get from these group numbers. In fact, you could look at the Roman numerals, and that also gives you the numbers. So group 1 is going to have 1 valence electron. Group 2 is going to have 2 valence electrons. Group 13 is not going to have 13, but it is going to have 3. 14, 4. 15, 5. 6, 7, and 8. So each of these groups then, 1 valence electron, 2 valence electron, 3, 4, 5, 6, 7, and 8 valence electrons for each of those groups. Okay? Now, that applies for everything in that group. So if I say group 18 has 8 valence electrons, that applies to everything down that group. Okay? Another thing that I taught you is oxidation numbers. And this is actually going to come back later, but I'll go ahead and give it to you again. I told you to add this to your periodic table, and hopefully you did. But these are the oxidation numbers. And that should look familiar to you all, okay? And so oxidation numbers are basically the charge that an ion of a particular element is going to be in order to get a full outer shell, okay? It is the charge that an ion is going to be in order for an atom of a particular element to get a full outer shell. So obviously, that's why our noble gases have an oxidation number of 0. They don't have to gain or lose electrons to get a full outer shell. But if we look right here at group 16, for instance, maybe we're looking at the element oxygen. If we look at oxygen, it has a total number of electrons when it's neutral, mind you, of 8. So it'll have 8 electrons. So there we go. There's a nucleus. There's our 2, 1, 2, 3, 4, 5, 6. So at that point, it has 8. It does not have a full outer shell. It is still missing 2 electrons to get a full outer shell. So what does oxygen have to do? Well, it's going to gain 2, 1 and 2. And when it gains those 2 extra electrons, that gives it an overall charge of -2. And so that's the case for all of these. If it's a positive number, that means that it lost electrons instead of gained them, because electrons are negative. If you have less electrons, there's less negative charge. So overall, you have a positive charge. It's all about balance. See, the thing is, if I look at the ionized version of oxygen, so this is O with a -2 charge, it's going to have 10 electrons, but it still only has 8 protons. And so obviously, because the electrons are going to be greater, okay, that means it has 2 extra. That's why you end up having a -2 charge. Okay, so anyway, let's get back to the table now that I've mentioned that, and I'll keep it kind of in frame over there. Okay, so alkali metals, that's group number 1, also known as group 1A. Oxidation number is going to be +1. Okay, number of valence electrons is going to be 1. So there we go. Okay, wow, great handwriting. All right, next group, it says it's group 2A. So group 2A, also known as group 2, is going to be alkaline, right? Alkaline earth metals. Alkaline earth metals. And that's going to have an oxidation. Well, I look over there and see group 2 has a +2 charge. Number of valence electrons. Looks like it has 2. Next one. Now, this is important. It says oxidation number varies and number of valence electrons varies. This is one of the groups that I told you guys was important. This is the transition metals. This is going to be more important in our next unit, but the reason it's special, okay, and it's right here. It's in the middle of the periodic table, okay? It's in the middle of the periodic table. The reason they're special is because they don't have a set oxidation number. Sometimes iron has an oxidation number of +2. Sometimes it has an oxidation number of +3. It just depends. And so the number of valence electrons changes as well. Group number, let's just say this is group number 3 through 12. Okay, and AB system is going to be 3B through 2B, technically, if you look at the way that it's written on the periodic table. Next group has 7 valence electrons. I know that means it's group 17 that I'm dealing with. And again, look at my chart over there. Okay, group 17 has 7 valence electrons. That's also going to be group 7A, written like that. This group name is going to be called the halogens. It's one of the groups I told you was important. Its oxidation number is a -1. I see it over there on my chart, and hopefully you have that on your periodic table located in your general folder. Okay, you have a reference table in your general folder, you should have that information written on there. Last one has an oxidation number of 0. That's because it has 8 valence electrons. It already has a full outer shell. This is group 18, also known as group 8A, VIIIA, and these are going to be the noble gases. Okay, let's continue. And I hope that if you're watching this, if you need to go back and rewatch it a second time, do that. If you need to pause it, pause it. All right, let's do some matching. Yay. Atomic radius. I'm going to go ahead and say that's the size of an atom. go out on a limb and say atomic radius is the size of an atom. So that's going to be D. Ionic radius. I'm going to go ahead and say that's probably size of an ion. E. Electronegativity. So you can check your notes on this, and I've talked about electronegativity a few times. It's the tendency of an atom to attract electrons, okay? Attract or hog is the word I keep using, okay? Being somewhat of a country person myself, I say hog it. It's going to hog it to itself. And so it's going to be A for electronegativity. Ionization energy is energy required to remove a loosely bound electron. It's the energy required to take that electron away. And then reactivity by process elimination. Oopsie. Well, I don't agree with that. Oh, I remember this. Perugini and I talked about this last year, and I told him he made a mistake, but whatever. I mean, reactivity is kind of that. I don't really like that definition. It says difficulty of removing an electron from an atom. I'd rather say it's the ability to combine with another element. But anyway, yeah, I remember having an issue with that last year, and I just forgot to fix it. But anyway, let's keep going. Fill in the blanks with either increases or decreases. Okay. You know what's really helpful when you do this? Your color coding that you should have done, because the second page has all these trends on it. Atomic radius is going to decrease from left to right and decrease from bottom to top. Okay, so there you go. There's your atomic radius. And it's because the pattern goes this way for atomic radius. It's going to increase as you go down and to the left as you get closer and closer to francium. So that's going to be your trend for atomic radius. Next one, electronegativity increases. Okay, so this increases from left to right and increases from bottom to top. And that's because the trend for electronegativity goes this way. Okay, electronegativity goes up and to the right until you get not to helium, but until you get to fluorine, which is located right there. Okay, so fluorine, well, hopefully it'll show up. Fluorine located right there. Seriously? There we go. And it's because your noble gases do not react, they do not bond. Electronegativity has to do with bonding. Okay. Next one, ionization energy. Ionization energy increases from left to right. Change the color on that. And increases from bottom to top. It has basically the same pattern as what we had for electronegativity. It's still going to increase as you go up and to the right, but this one does include helium. It does include a noble gas. It is really, really hard to get electrons away from noble gases because of the fact that noble gases have that full outer shell. They don't want to lose it. Next one, reactivity. So this one's kind of weird, I'll be honest. Let's just say, because it could be both. I would say it decreases, then increases from left to right, and just depends on what side of the periodic table you're on. So I don't know. Again, Perugini wrote this part of this, and I disagreed with it. But anyway. So the reason is it depends on what side of the staircase that you're on. So hopefully you guys remember the periodic The periodic stair step is right here on the periodic table. And so the fact is, if you're looking at reactivity, okay, it's going to go this way on the right side of the stair step as you get closer and closer to fluorine, not the noble gases. And on the left side of the stair step, it's actually going to increase as you go this way, as you get closer to francium. So that's why I'm saying reactivity is going to decrease from left to right, but then it's going to start to increase again. And honestly, I don't know. I'm just going to put NA because I like that answer better than anything else. If you're going from bottom to top on the left side of the periodic table, you would say it decreases. On the right side of the periodic table, you would say it increases. That's why I'm just going to say NA and move on. Next one, number 5, metallic character. Okay, metallic character. Your metals, in case you've forgotten, are all on this side of the periodic table over here, and your nonmetals are all on this side of the periodic table over here. So you got your nonmetals, you got your metals. So as you go from left to right, you're getting closer and closer to the nonmetal, so it's going to decrease from left to right. Okay, and in general, as you go from bottom to top, it's going to decrease as well because of that pattern with the stair step. So your most non-metallic element would be helium, but your most metallic element would be francium down and to the left. So once again, we see this pattern right here as you get down and to the left. All right. So that's not actually what we're doing down here on this periodic table. It says indicate on the blank periodic table the location of S, P, D, and F blocks. Not a problem. So my S blocks are over here. Sorry, I'm coloring. It'll show up in a moment. So there's my S blocks. And also helium. It's also an S block. So there we go. Check. Next one, P. Your P blocks. They're all going to be over here, okay, on this side of the periodic table. All right, I can probably do better than that. There we go. Beautiful. Okay, hopefully you guys will see this in a moment. But anyway, there's our P blocks. D blocks. They're in the middle. They're the transition metal area. So D blocks are in the middle. And this should all be review for you guys, honestly, because I've mentioned it a few times. Quite a few times. This is actually from the last unit, and it's just something we reviewed this time around. And then lastly, we have the F blocks. I'm just going to use black because that's the only other highlighter color I have. So we'll just say here's my F blocks down here. Okay, there you go. Okay, let's move on. Fill in the blanks. Oh boy, I love fill in the blank. Not really. Compared to a neutral atom, okay, it's... Oh, I see. So you've got to remember we have cations and anions. This is something that's worth, I don't know, it's worth going over again. We've got a cation. We're also going to have an anion, which I like to joke and call it cation and anion. But your cation, okay, has that T in it. And that's the way that I remember. Seriously, that's how I remember this is positive. So if this is positive, it's positive because it loses electrons. And the anion, okay, or anion, pardon me, is going to be negative. And it's because it gains electrons. Now, you've got to think about it this way. If you're looking at a neutral atom, okay, so anyway, there's a nucleus right there. If you're dealing with your number of electrons, and maybe, I don't know, maybe you start with, maybe it's like carbon, okay? Carbon has 6 electrons, okay? And so we can see that there's its orbit, okay? There's its orbits. Now, this is what's important. In a cation, you lose electrons. So if you lose electrons, say you drop down to a full outer shell and you lose this outer bit. See how much smaller that is? When it loses those electrons, it has to drop down. The whole size gets smaller. Well, the opposite is your anion. In general, if you're gaining electrons, okay, in general, if you're gaining electrons, it's going to be a little bit bigger, okay? So its anion radius is larger. I'll write that down here. And its cation radius is smaller, okay? Metals tend to lose electrons, okay? And if you don't believe me, you can look at our oxidation numbers. Over here on the left side, we have oxidation numbers of +1, +2, and +3 on the metal side, and it's because they're losing electrons in order to gain stability of a filled, it says octet, which is actually a word that I'm not sure I mentioned or not. Octet, as the name implies, think octet, think octopus if you want, which is not a word I've had to spell lately. I guess that's right. It has 8. Okay, so you're looking for 8 out of 8. That's what octet means. So full outer shell, same thing. Number 3, the greater the blank of an element, the lower the ionization energy and electronegativity. I'm going to go ahead and say metallic character. Yeah, it's the only one that fits there. Honestly, I would have preferred that this said atomic radius instead, because the bigger your atomic radius, the further the electrons are from the nucleus, and it's easier to pull them away because they're not as strongly attracted to the nucleus. So I would have rather have said that, but whatever. Metallic character is an option. The larger the atom is, hey, there we go, the more blank it is. okay? It's going to be reactive. And that's how willing an atom is to share, gain, or lose electrons. Okay, there we go. Next part, this is a part that a lot of students struggle with, and it's review, so I'm really confused why you did. Fill in the orbitals in the electron configurations below for a neutral atom of the following elements. Excuse me, pardon me. So if we're dealing with neutral, and that's kind of a key word here. Sorry, let me get my tablet to cooperate. If we're dealing with the word neutral, that means that it's going to have the same number of electrons as it does protons. That means, oops, why did I write an N? Number of protons is equal to number of electrons. And so like if I look up sulfur, for instance, sulfur has an atomic number of 16, so that means it has 16 protons. So that means we're going to have 16 electrons. I look over here at rubidium. Rubidium, Rb, has 37 protons. And so if it's neutral, that means we're going to have 37 electrons. Okay? So all that being said, I got to find a place to put all these electrons. So as we've done in the past, when you do these, remember you start with the lowest energy level first and then work your way up in order of increasing energy. And so I'm going to start filling it out. 1s is going to have 1 and 2. Notice I'm doing an up and a down arrow. This should be something familiar for you guys. 2s up and down. 2p. Now remember, when I fill these out, I like to do up, 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 down, 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 like so. So at this point, let's pause and see how many I've dealt with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There you go. And notice right here in the 3P, you guys can hopefully see that, I did 1, 2, 3, up, 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 and then the fourth one went down. Okay, so there's what we have. Let me double check, make sure I did that right. So I ended on 3P4. Yeah, that's right, because I ended at sulfur. Okay, next one, let's look at rubidium. Same thing, but now I got to do it for 37. Oh man, Mr. Nairn gives us so much work making us do 2 whole orbital diagrams. So I'll go ahead and get caught up real quick. I'll let you know where I'm at. So right now I'm at 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now I go over here to 3D because look, technically 3D is lower than 4P, so we're going to fill in that one next. And now I lost my count. Hold on. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. How many have I got? 37. 33, 34, 35, 36, 37. Good gracious, that's a lot of arrows. But again, I did it in order of increasing energy. I started from the bottom and worked my way up. Okay? All right, so now that we did that, let's take a look at the next part. It says, write the electron configurations for each, and it specifically says, use the noble gas notation. Because the thing is, I could go in for sulfur and start running out and saying, oh, I got 1s2, 2s2, 2p6, 3s2, ooh, that was a good 2, and then 3p4. I could, but that's not what the question's asking for. And a lot of students, those of you that didn't skip this, a lot of you went and did the full thing. Don't do that. Remember, you look on the periodic table and you say, okay, sulfur is right here. The last noble gas that we passed, okay, was up here at neon, because you work your way around. Let me go full screen for just a moment, and hopefully this will make more sense. Can I go to full camera? Here we go. So the thing is, if we're looking at the periodic table, okay, you always start over here with 1s1, 1s2, 2s2, blah, 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 2p, blah, 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 and you kind of keep going, keep going, keep going. But the thing is, if sulfur, sorry, it's backwards and reverse. So if sulfur's right here, the last gas that you passed on the way there was actually neon right here. So you went neon and then went on down the other side. So what we do when we do these then, for sulfur for instance, is I'll start by writing neon, okay, Ne, and then what I'll do is I'll say, all right, it's neon and then 3s2, and then 3p4. So it's like we're saying it's neon, which in case you've forgotten, okay, neon is going to be 1s2, 2s2, 2p6. See, that's the notation for neon, but instead of writing all that out, we just say, nope, it's Ne. And that's what we plug in up there. Rubidium is the same. See, you'd be writing all day if you wanted to do rubidium, talking about where 37 electrons go. But instead, just say, all right, rubidium, that's going to be krypton. Okay, and if you don't believe me, you can look at your periodic table. But it's going to be krypton, and then 5s1. That's it. Oops, why did I write a 2? I said 1 and then wrote 2. There we go. So it's going to be 5s1. Okie doke. So now that we've got that taken care of, I hope that makes a little more sense. I know that's kind of review, but now we're using it again. So down here in this table, okay, we're using that shorthand electron configuration, and then we're going to fill out some information about it. And again, this is based on stuff we've been doing for a while now. Now, I have to admit, this really frustrated me, and I had to go walk around the room real quick, but a lot of you did this. You looked at that electron configuration, saw where it said He, and said, oh, well, I must be dealing with helium. No, that is not how you do that, okay? That means that it's going to be helium. That's correct. You're going to have helium, but then 2s2, 2p4, oxygen. You're using the shorthand noble gas configuration to find out what it actually is. So it's not going to be helium. It's going to be oxygen. Okay, so that's going to be oxygen. I'll do the next one as well. So look, we find neon. It's all right. It's neon, 3s2. So it's not sodium. It's not magnesium. And then it says 3p2, aluminum, silicon. Oh, that one's silicon. I'm just following it out. And for some reason, it's not updating stuff on my screen. I'm writing this, and it's not updating on the screen. There's no reason for it to be doing this. Sorry, y'all. Please sync this notebook. Please do your job while I'm trying to help my students. Hopefully it'll load in a moment. Yeah, there we go. And then the last one we have is argon 4s1. So that's going to go ahead and be potassium. If you don't believe me, you can look. Okay, here's argon right over here. Right there. So here's argon. And then I'm not going to stop at argon. We're going to go till it says 4s1. It's potassium, 4s1. Okay, number of valence electrons. And I'm using, when I say number of valence electrons, I'm using, oh, don't do that. Come back. I'm using what we did before. Okay, this little table I made before, that's what I'm using. Because if I look up here, okay, oxygen, it's going to be in group 16. It's right there. Potassium. Oh, come on. There's no... Sorry, y'all. I'm not going to get frustrated. I'm just going to go keep doing my job. There's oxygen. The next one's silicon. Silicon is in group 14, so it's going to be right there. So we got silicon, we got oxygen, and we have potassium. Okay? Potassium is over here. And so I'm going to use that information, okay? And again, you guys have this reference table. You have a reference table. I've told you to fill in this information. And if you haven't, I don't know why you haven't. That's answers. It's easy answers. Okay, so that being said, oxygen, because it's in group 16, okay, think about it this way, because it's in group 16, it's going to have 6 valence electrons. So I'll go ahead and write 6 valence electrons. Silicon. Silicon, as I just said, is in group 14, okay, so it's going to have 4 valence electrons, okay, and then potassium's in group 1, it's going to have 1 valence electron, okay, so this is all stuff that we've talked about before. Oxidation number, same thing, you should have this written on your periodic table. Starting on group 1, it goes +1, +2, you skip the transition metals, +3, plus or minus 4 in group 14, -3, -2, -1. So you should know those oxidation numbers by now. So if this is in group 16, it's going to have a charge of -2. If silicon is in group 14, it's going to be plus or -4. Okay, so silicon is special. Next one we have potassium is going to be +1 because it's in group number 1. And then we get to this. number of electrons lost or gained during bonding. So if I look at an oxidation number of -2, I know that electrons are negative. That's whenever I write electrons, I always write E with a little negative symbol. So if I have an overall charge of -2, I know that it gained electrons. I know that it gained electrons because it has to be a little more negative to do that. Now, I'm going to skip silicon. I'll come back to it. Potassium has a charge of +1. It is not going to gain protons. If it gains protons, it's not potassium anymore. Potassium has to have 19 protons. If it gains a proton, it's not going to be potassium, it'll be calcium. But it can lose electrons. It loses 1 electron. By losing 1 electron, protons and electrons are not balanced anymore. So if you lose an electron, now we have more protons, more positive protons. So that's why it's +1. Silicon could be gain or lose. It's special, and it'll make more sense once we do the Bohr model. So let's go ahead and do Bohr models. So nucleus is that inner circle. So I'm considering this right here. You know what? Let me make this a little prettier. Can I make this work? Yeah. So that inside circle we're going to say is the nucleus, so I'm not going to use that. Okay? But what I am going to do is put my electrons down. Okay, so here we go. Here we go. So oxygen. Okay? Normally, oxygen has 8 electrons. So that's 1, 2, 3, 4, 5, 6, 7, 8. However, if it gains electrons, okay, if it were to gain electrons, then it would have 2 extra electrons right there. And I'm going to leave them as hollow. I have to say, I gave you an electron configuration that says you should only have 6 valence electrons. By the way, how do I know that? Well, there's 2, there's 4. That's going to equal 6 electrons in the outer shell. But if it was the ion, that's what that means. -2 means it will gain 2 electrons. Now we look at the next one, silicon. Okay, silicon. Silicon has a total of 14 electrons when it's neutral. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so see, at this point with silicon, I could either gain 2 electrons, okay? Maybe we gain, or 4, 1, 2, 3, 4, and then it has 8 out of 8, right? Then it would have 8 out of 8 in the outer shell, and we'd be happy. But I could also lose, sorry, let me get it back. But I could also lose 4, because if I lose 1, 2, 3, 4 on the outer shell, look, now we're at 8 out of 8. We're good. So you could do either. That's why this one's kind of special. So I'm just going to leave it like that because that's the neutral silicon, not the charged version. And the last one we have is potassium. Okay, last one we have is potassium. So potassium has 19 electrons regularly. So let me go ahead and do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. And so as we can see, right now, if I were to stop right there, I would have 9 out of 8. And that's not good. And so that's why we say that if it wants to become charged, see, don't get me wrong, that's neutral. At this point, if I were to stop and count everything up, I'd have 19... What in the heck was that? Sorry. If I were to stop right there, I would have 19... Oh, the shape thing is on. Sorry. It would have 19 electrons, which is equal to 19 protons, and so we'd say, oh, that's neutral. But the thing is, if I lose 1 electron, that does make it so I have 8 out of 8. See, look, I'll remove that 1 right there. Now, all of a sudden, I have 8 out of 8, and we're good. But I don't have 19 electrons anymore. Now I have 18. And so if I have 18 electrons, It's not going to be equal anymore. It's not going to be neutral anymore. Because I have more positive charges, it's going to have a charge of +1. So I say all that to do this. Silicon, or potassium, excuse me, if it's neutral, it's going to look like that right there. It's going to have 1 extra on that outer shell, so it'll have 9 out of 8. Okay, let's keep moving. Circle the one in each group with the larger atomic radius. So I think it's worth doing this, just as a reminder. So atomic radius, it's going to be bigger as you go down and to the left as you get closer to the element francium. Okay, this should be familiar. I've mentioned it about 10 times now. So down and to the left. And so we're just going to look. We're going to look for each of these. So let's start with the first one, bromine or potassium. So potassium's up here. There we go. There's potassium. Bromine is way over here. I mean way over there. So there's bromine. So obviously, which one's closer to francium? Potassium. Next, lithium or calcium. Okay, well, calcium, I know, is right next to potassium. So we'll go ahead and put that calcium there. And then lithium is actually up here. Now, this is kind of tricky, okay, because you want to say, oh, well, lithium's an alkali metal. It's going to be that. But calcium's actually much closer. In fact, I should have sodium in between right there, so really I should move that down a little bit. It's really down here. There's my calcium. So see, because calcium's closer, I'm going to go ahead and say calcium is the answer, okay? Next one, francium or fluorine. Well, since francium is the largest atomic radius, I'm going to go ahead and say it's francium. And then the last one, we have sodium or magnesium. So sodium's right here. Magnesium's right next to it, right here. But as we can see, because sodium is closer, because it's an alkali metal in the same group as francium, sodium is going to be more reactive, have the larger atomic radius. Next one, circle the one in the group with the smaller electronegativity. Smaller electronegativity, just to make sure you're paying attention. So let me remind you guys again, electronegativity is going to increase as you go up and to the right, as you get closer to fluorine. Not the noble gases. They are not electronegative because they don't bond with anything. So now that we've done that, okay, it says circle the one in each group with smaller electronegativity. Smaller. Got to remember that. Otherwise, I'm going to mess up. Potassium is over here. Hey, it's the same ones as before. Bromine is way the heck over here. And so because bromine is closer, it would have a higher electronegativity. But I'm selecting the one with the smaller electronegativity. So it's potassium. Oh no, I think this is going to end up being basically the same answers as the last one. Anyway, we'll go through it anyway. It'll be fine. It'll be great. Sodium is going to be right here. Okay. And magnesium is going to be right next to it in Mg. Magnesium is closer to fluorine. Magnesium has higher electronegativity. So sodium has the smaller electronegativity. Fluorine's way the heck over there. Francium is down here. Francium is much smaller electronegativity, so it's francium by a long shot. And then the last one is lithium or calcium. Okay, so let me put lithium right here, because that's where it goes. And calcium is actually right here. Okay, now, this one's kind of tricky because lithium is higher up the periodic table, even though calcium is technically one closer to fluorine. Lithium and fluorine are in the same period, and I know it's hard to tell from my terrible drawing, but you can see lithium is right here, fluorine's right there. They're in the same period as one another, and so technically I would argue the lithium is going to be closer to fluorine, making it have a higher electronegativity. So if lithium has a higher electronegativity, calcium is going to have the lower, or the smaller electronegativity. Okay, guys, I hope this was helpful. I hope that some people watch it. That is everything you need to know for this test. In fact, tell you what, if you took the test and now you're just now watching the video, retake that test, and I'll give you the higher grade of the two. Anyway, I thank you guys. If you need anything, please contact me.